In this lecture, let's understand the junction physics. This junction physics will really help you while you will understanding the MOS physics, because in MOS also you have a junction between metal, semiconductor and oxide. Here I am considering a junction between N-type semiconductor and a p-type semiconductor. Okay, so these are the band diagram of N-type and p-type. In N-type you have a, let's say this is a valence band, you have a conduction band, and let's say you have a extrinsic Fermi level position is this could be with respect to EI, this could be with respect to EI, the intrinsic Fermi level. Okay, so when you make a contact between the p-type and n-type semiconductor, what happens is, because of this contact, because of these junctions, the following phenomena occurs. Whenever we will be studying any junction physics, let's say we are making a junction between two different material, for example in this case p-type and n-type, the following phenomena will definitely occur. If these materials has a difference in their Fermi level positions, definitely there will be a bending. There will be a bending when you will make a contact of these two. So definitely this bending, you can see this bending. So there will be a bending, because in equilibrium the Fermi level must align of the two side of the junction. The second thing is depletion region at the junction. So because there is a difference in Fermi level, there is a difference in the potential of electrons on both sides, so there is a movement, and after a certain period of time there is a equilibrium. After equilibrium you will find that there is a depletion region. Always there is a depletion region. And then the third phenomena will always occur whenever you will be having a junction, the depletion region charge. So in the depletion region, both sides you will be having a fixed ions, because for example in this case this is an n-type semiconductor. So n-type semiconductors has lot of majority of electrons, so these electron when will go towards the p side, they will recombine with the hole. So whenever one electron will go from n side to p side, it will leave behind a donor ion. Similarly, if this electron will get recombined with the hole which is there in the p side, it will leave behind the acceptor negative ions. Okay, so definitely there will be a fixed charge density in the depletion region. We have to take care of that depletion charge density. Then there will always be a built-in potential. Built-in potential meaning this height from this flat band to flat band height. So this height is known as a VBI. Always this will be occurring. So we need to find out all these four things. How much is the band bending? So what will be the depletion region at the junction? What will be the width of depletion region basically, and what will be the charge density, charge fixed charge ions in the depletion region, and what will be the built-in potentials. Okay, so let's find these three: depletion region charge, and the built-in potential. Bending will always be occur, which can be visually seen whenever you are making a p-n junction. You can visually see that there is a bending. Okay, now let's consider first the built-in potential. So what is the built-in potential? So the difference between the Fermi level of two sides. So for example we have a n side, so in n side you have a Fermi level somewhere over here, in p sides you have a Fermi level somewhere over here. So we know this distance, we already know the intrinsic to EFN minus EI, this we already know. This is what? This is KT by Q ln ND by NI, let's say. Okay, and what is the distance of this from EI to this distance? So this distance is always KT by EQ ln NA by NI, if we ignore the negative sign. So what will be the sum of these two? So when you will sum of these two, so KT by Q will be common, and this will become ln NA ND by NI square. So always there will be a built-in potential which is equal to NA ND divided by NI square. So that means the built-in potential completely depends upon the doping of both sides. So if you will be having a heavily doped p-n junction, the built-in potential will be higher. If you have a lightly doped p-n junction, the built-in potential will be lower. Now what will be the depletion charge, depletion region width? This is also a very important concept which will be which we will be using somewhere in MOS physics also. So what will be the depletion region width? So this width, so let me go back to that slide and let's understand. So this width, I'm talking about this width. So this is the width. So this width is always equal to, W equal to 2 epsilon SI divided by Q, 1 upon NA plus 1 upon ND VBI minus VA. Here VBI is the built-in potential which you just now calculated. It is a KT by Q ln NA ND by NI square, and VA is the applied voltage if any. If there is no voltage at equilibrium, the W will be, so at that time VA will be 0. So W will be 2 epsilon SI divided by Q, 1 upon NA plus 1 upon ND VBI. That's it. Okay, so where VA is the applied voltage, positive for forward bias, negative for reverse bias. So in this case, let's say if you are making a junction between two material, and let's say ND is very high than NA, which is normally the case in case of a N-channel MOSFET. In N-channel MOSFET, what happens is you have a gate which is a heavily doped polysilicon, heavily doped. The doping density of ND is very high. So in that case, NA is very small compared to ND. If you will keep this in this, then what happens is 1 upon ND becomes almost 0. So what you're left with, W equal to 2 epsilon SI divided by Q, 1 upon NA VBI minus VA. What will be the total charge in the depletion region? The total charge in the depletion region will be the charge of 1 electron into the total number of dopants, Na, into the width of the depletion region. So if you wanted to find out the charge in this region, let's say for example this is the depletion region, so the width of the depletion region is W, and what is the doping concentration per centimeter cube, and what is the charge of 1 electron. So when you will be having this, by keeping the value of W over here, you will get Q equal to 2 epsilon SI QNA VBI minus VA. So for rest of the MOS physics or MOSFET, we need to understand that whenever we are making a junction between two materials, there is always a depletion region, there is always a built-in potential, there is always a depletion region charge density, and the depletion region charge density is always 2 epsilon SI Q by NA VBI minus VA whole square root. Okay, so thank you very much.